All right, so let's take a look at vectors versus scalars. We're going to go over what the difference of those are. And then also talk about momentum today, a topic we haven't discussed in a while, so I thought it'd be useful to review that before your MCAS. So vectors and scalars are just special words we use to describe objects in physics, quantities in physics. And the main difference, the main thing you need to remember is anything that needs a direction is a vector. So all things in physics will have some sort of size, or what we call magnitude. If you see this word magnitude, very important to remember, that means the size. So in this example, 20 meters per second north, 20 is the magnitude. But this also has a direction, north. So this is an example of a vector. 20 meters per second north is a vector. That is a velocity. Velocity is a vector. That's different from something like speed. If you look down here, speed, in this example down here, 20 meters per second is a speed, and that's just size, magnitude. How much is the speed? 20. Magnitude, the size. So 20 meters per second. Same magnitude as this velocity up here, but speed is a scalar. It does not need any direction associated with it. So that's the main difference. Scalars do not have direction, do not need direction, and a vector in physics is something that needs direction. So common vectors, again, anything with a magnitude, a size, and direction include velocity, force, that's why we draw forces as arrows, they have a direction. Acceleration, you could have acceleration in a positive or negative direction. Negative direction would slow you down, you would have a deceleration. Displacement, remember that's how far from the start, so direction is important. If you come back to the start, you're subtracting and you get zero displacement. So these are all vectors, things that need magnitude and direction. Anything that does not need a direction is called a scalar. Common scalars, mass. So the mass, the amount of stuff, does not need a direction. Temperature does not have a direction. Distance, even if you're traveling back and forth, for distance we just add the total. We don't care about direction. And energy does not have a direction associated with it. So these are all common scalars. So these are things you should know and remember. So make sure you study these notes. Here's an example problem. Which of the following is an example of a vector? Well, if I read each answer, and I could see A, student walks 2.0 kilometers north. We have a direction here. Let's look at the other ones. B, an object has a mass of 10.5 kilograms. Mass, no direction. Okay, C, a 1.0 kilogram object moves at 18 meters per second, but no direction. D, a ball has an instantaneous speed of 15 meters per second. Again, no direction. So for vector, I'm looking for the one with the direction, which would be A. So this would be the displacement of a student, 2.0 kilometers north. I know this is a vector because it has a direction north. Which I found is a scalar quantity. So now I'm looking for the opposite. I'm looking for something that does not need direction. Now this one's a little tricky because you'll notice not all the answers have direction. So A, the mass of a brick. Okay, no direction. That could be scalar. B, the velocity of a falling tennis ball. Now it's not telling me the direction. I have to remember that velocity is a vector. Velocity is like speed but with direction. So I'd have to remember that so I would know that B is not the answer. C, a force required to lift 10 kilograms. Again, no direction, but I need to remember that force needs direction. That is a vector, so it won't be C. And D, acceleration. Again, I need to remember acceleration is a vector. So sometimes in MCAS, you got to remember what things need directions and what don't. So hopefully you'd get A, the mass of a brick is a scalar quantity. It does not need direction. And finally, which of the following is a vector quantity? A, mass, B, force, C, temperature, D, kinetic energy. Again, you have to remember which of these need direction and which do not. And the only one that needs direction, if you remember, forces are drawn as arrows. Forces have direction. The force could be up, down, so that is a vector quantity. So I recommend that you really try to study these notes on vectors and scalars. You'll see one or two questions about that. That's something you should know. Sometimes an open response question even. will relate to vectors and scalars. And it's just a way in physics to classify things. Does it need direction? It's a vector. Does it not? It's a scalar. So part of what we're going to review today is momentum. Momentum. What is momentum? So here's a question. To calculate the momentum of a pickup truck, velocity of 25 meters per second east, it's necessary to know which of the following. So we have time, drive force. People like that, has force. People think, oh great, force, that must be it. C, mass of the pickup. D, distance. So we have a velocity. We need to know what else do we need to know to find momentum. So what we're going to do is look at our steps here. Our steps for finding how to figure out something if we don't remember. Maybe you don't remember what momentum is. So you need to basically figure out, okay, is momentum on my formula sheet? What's the letter for momentum? Let's look up that letter and find what we call a variable. That's technically the right term. Find the variable or letter for momentum. Find the equation for it or formula. And then write it and then read it as a sentence. So if we look on the formula sheet, the letter for momentum, and you should pause and look for this yourself to get some practice. Hopefully you did that. Hopefully you paused it and looked and saw for momentum. All right, what we're looking for is this formula. P is for momentum, and as you look, the formula is mv, m for mass. If you don't remember what m is, look it up on your formula sheet. Lowercase v for velocity, not capital V, which is voltage, lowercase v. So here it is. So we need velocity, which they give us. We also need mass. So the answer would be C. To find momentum, you need mass and velocity. And here's a reminder, basically going back to scalars and vectors. Velocity is like speed, how fast, but also has direction. So now that we remember momentum is mass times velocity, we could solve and figure out momentum problems by using the formula you already hopefully looked up. So here's one, a 6-gram basketball, a 57-gram tennis ball, and a 46-gram golf ball, and a 2.7-gram table tennis ball are moving at the same velocity. What has the greatest momentum? Okay, so since they all have the same velocity, we're looking for the one with the biggest mass, because they're all moving with the same exact speed and direction, because velocity, speed with direction, so they're all going just as fast. So the only thing that would really affect their momentum is the mass. So to have the most momentum, we need the biggest mass. That would help us multiply by the biggest number, get the biggest answer for momentum. So the basketball out of these options has the largest mass out of all of them. There's another one. Now you actually have to solve. When you see numbers as your answer, here's a hint on the MCAS, and you see numbers as your answer, you better have your calculator and formula sheet ready. You're going to be calculating. So what is the momentum of a metal disc? We have the mass, 1.5 kilograms, sliding on a frictionless surface at 0.75 meters per second. So simply we're going to get that equation, that formula, put in the known values, what's given to us, to solve for the unknown, substitute and solve, and make sure you put the units. Now, if this was an open response, for multiple choice, they give you the units of momentum. It's a combination of mass units, kilograms, and velocity units, meters per second. But if this was open response, you need to make sure you include units or they will mark it wrong. So we take our mass, we take our meters per second. Remember your units. They don't tell you this is the velocity. You have to remember meters per second is for velocity. And so we have what we need. We use our formula to multiply and get 1.1 kilograms per meters per second. Okay? Now, here's a problem where they're dropping a block on an object that's moving to the right. And they want to know, okay, what happens to the velocity after? And we kind of messed around with carts this year and changing what happens when the mass changes as the cart's rolling. So this is going back to conservation of momentum. Conservation means whatever we start with, we got to end up with the same amount. We're not going to lose momentum. Momentum is conserved. Just like conservation of energy means the total energy stays the same. It's conserved. So the mass times velocity before, that's momentum, has to equal the mass times velocity after. So whatever it has for momentum before this event is going to have for momentum after. And since we're increasing mass on this side, in order for this side to equal this side, if the mass gets bigger, hopefully you understand that the velocity has to get smaller. Okay, I can't multiply by a bigger number and get the same answer unless I multiply that bigger number by a smaller number, right? So we have a smaller velocity here times a larger mass. So just thinking about that. So the cart will move to the right with a velocity less than the original velocity of the cart. All right, the only way this momentum would be the same, conserved, is if it's slowed down. And this happens in real life. If you add a block to a car that's moving, you'll notice it will slow down. And that has to do with conservation momentum. If the mass increases, the speed must decrease in order for momentum to be conserved. So you have your notes, conservation momentum. And you could actually use conservation momentum to solve collision problems. You could set it up to solve for the mass of an object or the velocity of an object after a collision. If they bounce off, that's called elastic. If they stick together, that's called inelastic. So look at this one. Now, just thinking about it, 1 kilogram has a speed of 2 meters per second. Interestingly, use speed instead of velocity here, but sometimes the MCAS switches speed and velocity without really thinking about it, but that's okay. The second 1 kilogram box going to the left, so both the same mass. One's going 2 meters per second. The other one, they're like, hey, what's going to be after the collision? Okay, after the collision, they're motionless. That means they stop. So what was the speed of this block? What speed does this block have to have in order for them to stop? Well, it's a collision. So they're giving us mass, velocity. So when you see mass and velocity, hey, that's momentum. You should be thinking about momentum. Mass and velocity, that's momentum. And we have a collision, so we're talking about conservation momentum. The momentum before has to equal the momentum after. Okay? So the total momentum of object 1 plus total momentum of object 2 is going to equal 0. That's the momentum after. If they're motionless, their velocity is 0, they have no momentum. So momentum before would be the momentum of these two together. And the momentum after is simply 0 because they both stop. So in order to get 0 for our answer, all right, so we have a mass of 1 times the speed of 2. So that gives us 2 over here. Now let's figure this one out. Mass of 1. And well, what's the speed have to be? So this will be 0. Well, think about it. We're trying to cancel this out, right? We're trying to cancel to get 0. Right? We need to get 2 plus this, whatever this velocity will be, equals 0. Well, the velocity has to be a -2, right? 2 plus -2 equals 0. Now, interesting, they don't give a -2 for the answer. This should be a negative answers up here. The MCAS is interesting sometimes. So just going back to it. So yeah, the answer would be the 2 meters per second. Technically, it should be -2 meters per second. But hey, I don't know. It's going in the negative direction to the left, but I'm not going to argue with the MCAS. As long as you know, hey, it has to be the same number to cancel out. That's what we're looking at here. Trying to get it to be the same momentum before and after. Total momentum before is total after. Well, the total after is 0. So how do I make sure the momentum before is 0? These have to cancel out. So it has to be going the same speed. If it was going faster and it collided, then this block would start moving to the left. If it was going slower and it collided, then this block would push this one to the right. The momentum would be slightly different. But since they have equal masses and we want the momentum to be 0, they have to have equal velocities. So that's basically one way to think of it. So the answer is B. And that's it for the notes. Now you're going to try some on your own. Good luck with your scalars, vectors, and momentum today. And yeah, have fun.